Hello everyone. Today we are going to see some more concept in statistical machine learning. My name is Dr. Amit Kumar Yadav, Assistant Professor, School of Computer Science and Artificial Intelligence, SR University, Warangal, Telangana, India. First, we will see uh, the basic concept related to say biological neural network. As we know that our brain composed of say 10 billions neuron and it has say 10,000 connection with other neurons. In this, each neuron receive and say electrochemical inputs from other neurons at say dendrite. If some of these electrical input is sufficiently more to activate the neuron, it transmits an electrochemical signal along the axon and it passes the signal to other neuron whose dendrites are attached at any of the axon terminus. Then these attached neuron may then fire. So we can say here neuron fire only if the total signal received at the cell body exceed a certain level. Here, the total input exceed a certain level, then the brain messes to perform extremely complex tasks. This is the model on which artificial neural network works. So here, artificial neural network haven't even come close to modeling the complexity of the brain, but they have shown to be good at problems which are easy for human but difficult for traditional computers such as image recognition and prediction based on past knowledge. Here first we will take perceptron. It is a mathematical model of biological neurons. Here, at the synapses between, say, dendrite and axon, electrical signals are modulated in, say, various amount. This is also modeled in the perceptron by multiplying each input value by a value called the bits. An actual neuron fires an output signal only when the total strength of input exceed a certain threshold. We model this phenomena in perceptron by calculating the weighted sum of input to represent the total strength of input signal, and we have to apply here a step function on the sum to determine its output. As in biological neural network, this output is fed to other perceptron. Now, try to see the figure of say biological neuron. Here we are having soma. Next here we are having synapses, then axon, then here we are having this dendrite. So this is the say biological neuron figures. Now, we will see some of the similarity between, say, biological neural network and artificial neural network. In biological neural network, we are having soma corresponding to this. In ANN, we are having node. In biological neural networks, we are having dendrites corresponding to this. We are having inputs in ANN. Corresponding to CNN, synapses in biological neural network, we are having bits or interconnection in ANN. Corresponding to biological neural network axon, we are having output in say artificial neural network. Next, here try to see this figure. Here at inputs we are having x1, x2, x3 up to xm. And corresponding to each input, we are having connecting bit W1, W2, say W3 up to say Wm. At this point, it is just a summation point. So, what is happening here? Uh, So x1 into w1 plus x2 into w2 plus x3 into w3 plus xm into ym. So this is called as a net input, and it will pass through the to this activation function. Then we are getting here output. Output. So how we can write this net input? That summation of I is equal to m into say xi into say wi, and it will pass through this activation function. Therefore, this y is a function of say net input. Net input. So this perceptron model is used in say artificial neural network to calculate the output. Now here we will see say activation function. Here we are having input say A1, A2, AN. Connecting bit we are having W1, W2, say WN. This is called as a bias bit, here summation function. Then here we are having activation function. Um, Here we have to find out say net sum, and it will pass through the activation function, and here we will get the output. So so here are say different types of say activation function. First we are having say sigmoid activation function. So its mathematical expression say we are having say y is equal to 1 by 1 plus e raised to power minus of x. And sigmoid activation function varies from say 0 to 1. Then we are having hyperbolic tangent function. Here y is equal to e raised to power x minus e raised to power minus of x by e raised to power x plus e raised to power of minus of x, and it varies from say -1 to say +1. Then we are having this rectified linear unit. This is called as a ReLU function. What is the mathematical expression? Y is equal to max of say 0 comma x. Then we are having leaky ReLU function. Y is equal to max. Here it is not 0. In ReLU activation function, here it will be say alpha x comma x, where alpha is a small constant, example say 0.1. Then we are having exponential function, ReLU function. Then here y is equal to x. When x is greater than or equal to 0, then we are having y is equal to a e raised to power x minus 1, x is less than 0. So basically we are using activation function to model non-linear relationship between say input and say target variable. So what are say different types of activation function which we are using in say neural network? So this one is say step function. Step function mathematical expression is say if say z is less than 0, we are getting 1 0. If z is greater than or equal to 0, we are getting 1. It is given by this graph, and its range is say 0 to 1. Then we are having signum function. Here if z is equal to -1, if z is less than 0, and it is 0 if z is equal to 0, and it is 1 if z is greater than 1. Its range is say from say -1 to +1. It is given by this graph here. Then we are having linear function if z is equal to x, and is vary from say minus infinity to plus infinity. Here it is shown graphically by this way. Then we are having ReLU function. Here fz is equal to 0 if z is less than 0. Fz is equal to z if z is greater than or equal to 0. And its ReLU function range, it's a varies between say 0 to infinity. Then we are having this sigmoid function. Fz is equal to e raised to power x by 1 plus e raised to power x. In sigmoid function, range is from say 0 to 1. Then we are having hyperbolic tangent function. Here it is equal to e raised to power z minus e raised to power of minus of z by e raised to power z plus e raised to power of minus z. So it varies from say minus 1 say plus 1. Now, how we have to choose the activation function, right? So there are say different types of rules by which we can choose say different types of activation function. So for regression problem, we use a linear activation function. For binary classification, we are using say sigmoid activation function. For multi-class classification, we are using say softmax. For multi-level classification, we are using say sigmoid. And in convolutional neural network, we are using this ReLU function. Then we are having recurrent neural network. We are using say hyperbolic tangent or sigmoid activation function. Now we will see some example of this activation function. So if we take linear activation function, here output is equal to z. If z is equal to say 0.5, then your output is equal to say 0.5. In sigmoid activation function, 1 by 1 plus e raised to power minus z, if we put z is equal to 0.5, so we will put here, it will become 1 by 1 plus e raised to power minus of 0.5, and when we will solve this one, we are getting here 0.6225. Then here hyperbolic tangent and tan hyperbolic activation function. Here output is equal to e raised to power z minus e raised to power of minus of z by e raised to power z plus e raised to power of minus of z. If we put z is equal to 0.5, when we solve this one, we are getting here say 0.4621. Then here we are having rectified linear unit. This is called as a ReLU activation function, and its mathematical expression output is equal to max of say 0 point z 0 comma z. If z is equal to 0.5, then output is equal to 0.5. If z is equal to say minus of 0.5, then output is equal to 0, because here we have to take a maximum of say 0 and 0.5, and there will be the output. So here 0.5. If we take z is equal to minus of 0.5, so maximum of 0 and minus of 0.5, output is 0. Then here we are having leaky ReLU activation function. Here output is equal to max of alpha z comma z, and here alpha varies from say 0 to 1. If we take alpha as a 0.01 and z is equal to say minus of 0.5, then here output is equal to max of, we will multiply this 0.01 into z, say minus of 0.5. Here z is equal to minus of 0.5. When we are getting the maximum of these two, that will be equal to minus of say 0.05. So how it is different from say ReLU function, this leaky ReLU in form of this mathematical expression. Then we are having softmax activation function. It is used in the output layer for classification. Then if we take a vector of input size z, say z1, z2 up to say zm, here we are having output I, that will be equal to e raised to power zi by summation of j is equal to 1 to n. Here e raised to power zi. Example, if z is equal to this one, how output values, right? So first we will put here e raised to power 1.0, and then we will put here e raised to power 1.0 plus e raised to power 2.0 plus e raised to power 3.0. 0. So when we solve this one, we are getting here 0.9. Then we will take here e raised to power say 2.0 in the numerator, and we have to compute all this part. We are getting here 0.24. Then here e raised to power 3.0, and when we will compute this one, we are getting here say 0.66. We will try to solve one simple numerical related to perceptron. Suppose here we are having three neurons x1, x2, x3, or you can say the three node x1, x2, x3, and one neuron here y. And corresponding to x1 node, we are having 0.3 input and 0.2 connecting bit value. And x2, we are having 0.5 input and bit value say 0.1. And x3, we are having input say 0.6 and bit value say minus of say 0.3. So here solution say x1, x2 up to x3, we are having 0.3, 0.5, say 0.6. Then we are having W1, W2, W3. Here we are having 0.2, 0.1, say minus of 0.3. Right? So the net input can be calculated as say yin say x1 into say w1 plus x2 into w2 plus x3 into say w3. So when we multiply this one, say x1 say 0.3 into 0.2 plus 0.5 into 0.1 plus 0.6 into 0 point minus of say 0.3. When we will add all this part, we will get here net input that will be equal to minus of 0.07. Then we are having this macula split neurons. It is known as say threshold logic unit, and it is a simplified models of say biological neuron. It is proposed by say Warren Maculas and Walter Pitts in 1943, and it laid the foundation for development of say artificial neural network. Here, each input to the neuron is binary, meaning it can take on the value either say 0 or 1. Then here baited connection, each input is associated with bait, which represent the strength of connection between say input and neurons. Then threshold, the neuron has a threshold value. If baited sum of the input exceed this threshold, the neuron fires. Fires means output 1. Otherwise, it remains inactive, say output as say 0. Then here mathematically, the output of a macula split neuron can be represented as follow. Here y is equal to 1 if summation of wi into xi is greater than or equal to threshold, and it is 0 otherwise. What it means? Where y is the output of the neurons, xi represents a binary input, wi represents bait associated with input. Here summation of say wi into xi calculate weighted sum of input. Here the threshold is predefined and it is constant. Now try to see what is the difference between say biases and threshold. So in neural network biases, it is an additional parameter added to neurons. It represents tendency of neuron to fire when all inputs are 0. Mathematically, the bias is conceptually similar to the intercept in say linear regression. It allows neural network to fit more complex patterns by shifting the activation function curve up or down. Threshold, this represent a fixed value that the weighted sum of input must surpass for the neurons to activate. If weighted sum of input is more than say threshold, the neurons output the signals, otherwise it will be remain inactive or it will be zero. If sum of input crosses the decision boundary, the neuron decide to fire. Now here we are having input x. Here we are having connecting bit. Output is a function of say w naught into x. Here we are having no bias. In another case we are having say here bias here we put here. So what will be the output? F into say w naught into x plus w1 into bias value say b. Now we will see another numericals have been with bias value 1 and it's gonna and having this bait value say 0.45. So here we are having say x1, x2 and bias value we have written in say in matrix. What is say w1 say w2 here say 0.3 say 0.7. Next, the net input can be calculated as yn is equal to say bias value b plus x1 into w1 plus x2 into w2. So when we put all the values of bias here say 0.45, x1 x1 say 0.2, w1 say 0.3, x2 here say 0.6, w2 here we are having say 0.7. So when we put all these value here, when we will add all this value, we are getting here say 0.93. It is a say net input. So after this we will see what is say basic learning rules. It decides how network adjusts its parameter are based on input data and desired output during training process. So here there are say different types of learning rules. First one say Hebbian learning. It is say developed by Donald Hebb. It states that cells that fire together wire together. If two neurons are activated simultaneously, the connecting synaptic bed between them is strengthened. Hebbian learning we are using in say unsupervised learning scenarios where the network learn to recognize patterns without explicit label. Then we are having this error correction learning. It is also called as a delta rules. It is based on say supervised learning approach where networks adjust is based on say error between predicted output and say desired output. So the most common error correction learning is say delta rules. It is also known as a Bidrow-Hoff rule. Now here what are different steps? First we have to calculate the error, which is difference between say actual output and say desired output. Based on this error, we have to update the connecting bit W. Then we have to repeat the process iteratively until the error converges to an acceptable range. So these basic rules form the foundation for more advanced and complex algorithm used in say neural network training. Variation and combination of these rules such as backpropagation, stochastic gradient descent and say reinforcement learning. The choice of learning rule often depend on say type of problem, the nature of data and architecture of say neural networks. Then what do you mean by say supervised learning? It is a types of say machine learning where model is trained on say labeled data set. The main goal is to learn a mapping from input feature to a target output. What is key concept in supervised learning? First, say label data. So here data set contain input output pairs where each input is associated with a correct output. Features, these are input variables used to make prediction. In a data set, features are say independent variable that help the model learn. Target label, this is the output variable that model aim to predict. It is the say dependent variable in the data set. Training and testing, the data set is usually divided into two parts. Training set data is used to train the model. Testing data set, it is used to evaluate model performance on unseen data. Model, the algorithm are mathematical structures that learn the mapping from input features to target output. Loss function, it is used to measure how well the model prediction match the actual label in training data. The goal of the training process is to minimize the loss process. Here we are using the optimization algorithm like say gradient descent are used to minimize the loss function by adjusting the model's parameters. Next, what are say different types of supervised learning? So first we are having this classification. In this output variable is in say categorical. Example, yes or no. The model learned to predict category of an input based on feature. Its example comes a email spam detection, image recognition. Regression, where output variable is continuous. Example, say price, temperature. Model learn to predict a continuous value based on say input features. Its example is say forecasting stock prices, predicting house prices. Next, here we are having perceptron algorithm. It is one of the simplest type of artificial neural networks, and it is the foundation of many other neural network model. It is a supervised learning algorithm. It is used for say binary classification tasks where goal is to classify input data into one of the two classes. The input features algorithm take a set of say input features here x1, x2 up to xn. Weight, each input feature is assigned a weight value, say w1, w2 up to say wn. The weight determine the importance of each features in the final decision. Here bias B is added to the weighted sum of the inputs. It allows decision boundary to be shifted and is similar to the intercept in linear regression. The activation function here perceptron calculate a weighted sum of input, add the bias and then pass this result through an activation function. Here output is 1 if weighted sum is positive or 0 otherwise. Output, the final output is the prediction, which is typically a binary value indicating the class to which the input belongs. Then we are having perceptron learning. It aims to find the optimal weight and bias that correctly classifies the input data. The algorithm follows these steps. First of all, we have to initialize weight and bias. Start bit, random weight and bias often initialized to 0. For each training, compute weighted sum z is equal to say w1 into x1 plus up to say wn into xn plus bias. Then we have to apply activation function to determine the output. is equal to 1 if z is greater than 0, and it is minus 1 if z is less than or equal to 0. Update the weight and bias if output is incorrect. The updated rules say Wi I plus 1 is equal to Wi plus into uh, plus delta Wi, where what is the meaning of say delta Wi, where eta into y minus output into xi, where this eta is the learning rate, y is the true level, and xi is the input features. Then we have to repeat adjust the weight and bias until all data points are correctly classified or a maximum number of iterations is reached. Then we are having this single layer neural network. The single layer neural network, often referred to as single perceptron or simply a perceptron, is one of the simplest form of say neural network. It consists of say single layer of output neurons connected directly to the input features without any hidden layer. What are key components of single layer neurons? Input layers. The network receive input data x is equal to x1, x2 up to xn, where each xi represents a feature. There are no computations performed in the input layer. It simply passes the input features to the next layer. Then weight and bias. Each input feature xi is associated with weight wi. Additionally, is a say bias term b that help in shifting the decision boundary. The weighted sum of input plus the bias is computed as say z is equal to w into x plus b, that will be equal to W1 into X1 plus W2 into X2 up to say Wn into Xn plus bias. Then here we are having activation function is applied to the say weighted sum Z to produce the output. So in case of say single layer perceptron, it is used for say binary classification. A step function or a sign function is commonly used. Say y bar is equal to sign of z, and its value is 1 if z is greater than or equal to 0, and its value is minus 1 if z is less than 0. For other application, different activation function like sigmoid or ReLU may be used. The output y cap is the predicted made by the networks. And for binary classification problem, it will be labeled between say plus 1 and minus 1 or 1 and 0. So here we will see the single layer neural network for say binary classification. Consider a simple example with two input features say x1 and x2, and let's we are having weight say w1 at say 0.5, w2 as minus of 0.5, and bias value b as say 0.1. Suppose the input features are x1 is equal to 2, x2 is equal to 1. Here computed the weighted sum. We have to multiply the input with its corresponding weight. We will get here say 0.6. Then we have to apply the step function for binary classification. Here y cap is equal to here signum say 0.6. Here we are having say plus 1. So the output, the network predict the class as a plus 1. Then here we will see what do we mean by say features map. It is a concept used in say machine learning in context based say convolution neural network, which is given by CNNs and support vector machines say ESPM. Uh, Here, there is a transformation of input data into new representation that make it easier for model to learn and make prediction. So features map in say neural networks. So general neural networks, here feature map is created by applying a set of transformation uh, to input data. Each layer in the network learn to map the input features to a new features. There are more informative for tasks at hand, such as classification or regression. So consider an input vector, say x is equal to x1, x2 up to xn. A layer in neural network with bit W and bias B would produce a new features map Z by applying as a linear transformation by a non-linear activation function. Here Z is equal to f as a function of wx plus b. The new feature Z is then passed to the next layer for further processing. Then here features map in say convolution neural networks. Here in CNN features map are say output of say convolution layer after applying um, convolution operation to the input data. A convolution layers applies a set of filter kernels to the input maps image or features map to extract features such as age, texture, or other spatial uh, parameters. So try to see the example. Here input image is represented as a matrix of say pixel value. Then we apply the convolutional filter called as kernel filter is slide over the image and compute a dot product between filter and the local region of the image. The result of this operation is a feature map that highlights the presence of specific patterns, say dedicated by the filter. Here we are using say multiple filter produces multiple features maps. Each capture different aspects of the image. Then here we are having the kernel tricks. It is a fundamental concept in machine learning in say short vector machine that involves linear classification. Here there is a linear classifier and it performs a non-linear classification. The idea behind this kernel trick is to transform original data into high dimensional space where it is easier to separate the data point with a hyperplane. How it works? Input space versus feature space. Input space means original space where your data reside. Feature space, a higher dimensional space where data is mapped so that it becomes easier to separate using a linear decision boundary. Then we are having kernel function compute the inner product of two vectors in the features space. Common kernel function linear kernel k x comma y x dot y polynomial kernel here x dot y plus c raised to power d. Then we are having a radial function or Gaussian kernels here exponential of say gamma by mod of x minus y whole square. Then we are having this sigmoid kernels. It is given by tan hyperbolic into say alpha x into y plus c. Here SBM bit kernels, it allow algorithm to create non-linear decision boundaries in the original input space by using a linear classifier in the transformed feature space. The SBM optimization problem is solved in the feature space, but thanks to kernel trick, you only need to work in the original input space. Then what is the architecture of say neural networks? It consists of large number of artificial neurons. Yes, we are having these input layers. Here we are having hidden layer 1, then hidden layer 2, hidden layer, and then after this here we are having output layers. Input layers, it accept inputs in several different formats provided by the programmer. And on hidden layers, it is between say input and output layers. It perform all the computation to find hidden features and pattern. Then we are having output layers, which finally results in output that is conveyed using this layer. The artificial neural networks take inputs and compute the weighted sum of say input and includes an bias. How do artificial neural networks work? It is called as a weighted directed graph. It has certain direction. The association between, say, neuron output and neuron input can be viewed as a directed edge with weight. The artificial neural network receives the input signal from external source in the form of patterns and image in the form of, say, the vectors. So here try to see here input signal proceed in this direction, error signal proceed in, say, this direction. Then we are having this perceptron learning rule. So each connection in neural network has an associated weight which changes in course of learning. If we take example of say supervised learning, here calculate the output value on the basis of set of record for which we know the expected output. So here, first of all, we have to compute the sum of square error for each individual in the learning sample. Perform first summation on the individual of learning set, and then we have to perform the second summation on the output unit. So here, expected and or you can say the target and obtain output in the networks is calculated. So with the help of this error, the network adjusts the connecting bits. If error function has increased or decreased, so on this basis, connecting bit is adjusted between um, the layers to minimize the error. Then we are having this delta learning rule. It is developed by Bidrow and Hop. It depends on called supervised learning. So this rules state modification in say synaptic weight of a node. It is equal to in mathematical form delta w is equal to eta t minus y into x1. So for a given vector, compare the output vector is the correct answer. If the difference is zero, no learning take place. Otherwise, adjust the network to reduce this difference. Here we are having this parametric method. This is called as a linear regression. So here say multiple linear regression. Here we are having multiple predictor variables. Say here x1, x2 up to say xn. Then one dependent variable say y. Beta naught is the intercept and beta 1, beta 2 up to beta n are coefficient of say respective independent variables. Now, how we have to find out this least square estimate? So the objective is to minimize the residual sum of square. Here, yi is the actual value, yi cap is the say predicted value. R square here, goodness of fit, measure proportion of variance in say dependent variable that is predictable from independent variable. R square varies from say 0 to 1 with higher value indicate better fit. Adjusted R square uh, adjusted for number of predictors in the model, provided a more accurate measure when dealing with multiple predictors. Model selection, it is a process of choosing the best statistical model. It is a crucial step in say building predictive models. The goal is to select models that best generalize to new unseen data. Now, what are the key concepts in model selection? First, we will see underfitting. What do you mean by underfitting? It has a high bias and poor performance on both training and testing data. Then we are having overfitting. A model is too complex and capture noise. It has low bias but high variance, perform well on training data but poor on say testing data. Try to see this model. Here we are having, this is called as a underfitting, having high bias. Then we are having low bias and low variance. It is called as a good fitting. Then we are having high variance. It is called as a overfitting. Bias and variance trade-off. Here bias error introduced by approximating a real-world problem which may be complex by a simplified model. Variance error introduced by model sensitivity to fluctuation in the training data. The goal is to find a model that balances bias and variance to minimize overall error. The bias variance trade off is a fundamental concept in machine learning that describes the trade off between error introduced by bias of the model and error introduced by the bias of the models. So here, try to see here what do we mean by bias. Here, it reflects how much the model predictors deviate from the true value on average. High bias means high bias leads to underfitting, where model perform poorly on both training and say test data. Example of this one, a linear regression model used to fit a say complex nonlinear relationship with will have high bias. Variance, it measures how much the model prediction would change if we use a different training data set. High variance capture noise. It leads to overfitting, where model perform well on training data but poorly on say unseen data. Example of this one, say such as a decision tree with many nodes may have high variance. Bias variance trade-off. So low bias and high variance. Here overfit the training data. Model captures the noise in training data, leading to a low error on training set but a high error on test set. High bias and low variance. It's a underfit the data. Here, model fails to capture the underlying pattern in data, leading to high error on both training and test set. Optimal trade-off here to find a model that balance bias and variance. This model will generalize well to new unseen data. So try to see this figure. It is called as bias variance trade-off. So here this graph indicates a bias and this graph indicates variance. So in between this intersection we are having optimal model complexity. This is called as a bias variance trade-off figure. So regularization here, techniques like say lasso, ridge, and elastic net add penalty uh, for complexity to model. It helps say control variance and reduce overfitting. Model selection here, simple model example say linear regression might have higher bias but lower variance. While more complex model examples and neural networks might have low bias but high variance. Here cross validation help in estimating model performance on unseen data, providing a more reliable estimate of say bias variance trade-off. Then we are having say generalized linear models. Here generalizes the ordinary linear regression. It is used for various type of say regression analysis. Linear separability. Here here we are using say class or categories can be separated by say linear decision boundary. It means it is possible to draw a straight line or hyperplane in high dimension that completely separate the instance of one class from the instance of an other class. So here, this try to see this figure. Here, this is called as a non-linear separable because we cannot draw the graph, draw one line to separate between the not sold and sold. This is called as a linear separable because we can draw one line or hyperplane to separate between say not sold and sold. Then we are having this classification. It is a process of categorizing data or object into say predefined class or category based on their features or attribute. So here if we draw a line, so this is called as say classification 1 and classification 2. Binary classification, the goal is to classify the input into one of two classes or categories. Here, whether the person has certain disease or not. Multi-class classification, the goal is to classify the input into one of say several classes or say categories. Here, try to see this figure. This is called as example of say binary classification having two class. In multi-class classification, we are having more than two class. Okay, here this is one class, another class is this one, another class is this one. This is called as a multi-class classification. Now, linear classification, here, linear classification means a straight line or hyperplane in say higher dimension. What is the goal? Is to find a linear function that classify data point into two classes. This is achieved by finding the best fitting linear boundary. The mathematical equation here we are having linear classifier y is equal to w into x plus b, where w is equal to say base parameters of the model. X is the say features input variables. B is the bias term. Y is the predicted output. So here, if we take this example here example of say one dimensional, the linear classifier has a linear boundary. This is called as a hyperplane W naught plus W transpose x is equal to 0. We separate the space into two half space. In 1D, this is simply as a threshold. Example of say 2D here, the linear classifier has a linear boundary called as a hyperplane. Here W naught plus W transpose into x is equal to 0. We separate the space into two half space. In 2D, this is a line. Next, we are having say 3D space. Here, the linear classifier has a linear boundary. Here, we are having say hyperplane W naught plus W transpose into x is equal to 0. We separate the space into two half space. In 3D, this is a plane. What about say higher dimensional space? Then we are having this logistic classification. Here it is called as a logistic regression. It is a statistical method used for say binary classification problem. It is used to predict one of two possible outcomes. For example, it can classify emails or spam or not spam, or predict whether a person has disease, yes or no. The core of logistic classification is given by this logistic function 1 by 1 plus e raised to power of minus of z. This function maps any real value number to a value between say 0 and 1, which can be interpreted as probability of class 1, say positive class. Here, logistic regression uses a linear model to make prediction. The model can be expressed as say z is equal to w into x plus b. Here x is the feature vector called input variables. W is the say weight of is the vector of bits called parameter. B is the say bias term. Then in say linear classification, so here try to see the numerical, a basic numerical example of linear classification can be illustrated with a simple 2D data set. Let's use two classes of point, each with two features, say x1 and x2, and try to classify them using a linear classifier. The problem is to fit a linear classifier to separate these two classes. Say class 1 label as 0, class 2 label as 1. So here 1, 2, 2, 3, 3, 3. Here we are having class 2 label 5, 6, 6, 7, say 7, 8. Now, how we have to do the solution? First, a linear classifier can be developed as a fx is equal to w1 into x1 plus w2 into x2 plus b, where x1, x2 are the features of input data, w1 and w2 are the bit, b is the bias. The decision boundary is defined by setting fx is equal to 0, we simplify w1 into x1 plus w2 into x2 plus b is equal to 0. Then we have to formulate the objective function. For simplicity, let us assume we are using a method like perceptron or support vector machine to solve the best hyperplane. Calculate the decision boundary. So here we are having w1 is equal to 1, w2 is equal to 1, b is equal to minus of 1. The decision boundary equation, what we are getting here, by putting all these value of weight and bias in the equation, say x1 plus x2 minus 5 is equal to 0, or x2 is equal to say 5 minus of x. We have to solve this equation, nothing else. Then classification, if fx is greater than 0, then classify as a class 2, it is called as a label 1. If fx is less than 0, it is called as a class 1 and label 0. Let's classify a new point, say 4, 4. When we put here 4, we are getting here 3. So f4, 4 is greater than 0, so it is classified as a class 2 label. Next here, probability, the output z of linear model, and it is fed to a sigmoid function, okay, to get the probability. So it is given by say 1 by 1 plus e raised to power of minus of z. The final prediction is made by setting a threshold, typically 0.5. If probability is greater than or equal to the threshold, the instance is classified as positive class 1. Otherwise, it is classified as negative class, say 0. Next, we are having say support vector machine. It is supervised learning algorithm commonly used for say classification and say regression tasks. It works by finding optimal boundaries, say hyperplane that best separate the classes in feature space. Hyperplane here in SBM, a hyperplane is a decision boundary that separate data points of different classes. In 2D space, this is a line. In 3D, it is a plane. And in higher dimension, it is a hyperplane. Support vector machine are the say data point that are closest to hyperplane and are critical in defining the position and orientation of say hyperplane. These points are used to maximize the margin. So what do you mean by say margin? It is difference between hyperplane and say nearest data point from either class, the support vectors. It aims to maximize the margin to ensure that say data points are classified with say highest possible confidence. Linear versus non-linear SBM. So linear SBM here, here it can be separated by straight line or hyperplane. Nonlinear SBM, where data is not linearly separable. Here SBM use polynomial radial basis function to transform data into say higher dimensional space where it can be linearly separated. Kernel tricks is a method to transform data into high-dimensional space without explicitly computing the coordinate in that space. This allows SBM to create a nonlinear decision boundary. So here try to see this here numerical. Here we are having number of hour studies. It is given by x. Then we are having score y. Where our objective function find a line y is equal to mx plus c that best fit this data. Then first of all we have to create mean of x. It is given by 2.5. Then we have to create mean of y. Here we are getting 5. Then we have to calculate the slope m. Here it is given by summation xi minus x bar into yi minus y bar by summation of xi minus x bar whole square. When we will put all this value, we are getting here slope m is equal to 2. Next here intercept. Calculate the intercept. C is equal to y bar minus m into x bar. So when we put all this value here, we are getting say intercept value as a 0. Then we are having say regularization. So it prevent overfitting by adding penalty to the loss function during training. So how we can do this regularization? First one say L1 regularization. It is called as say lasso. Add the absolute value of the coefficient to the loss function. Here, what is the main effect? It encourages sparsity in model by driving some coefficient to exactly 0. What is the loss function here? Loss plus lambda by summation of say theta I. So you want to reduce the number of features used in the model. Then we are using say L2 regularization. Add the square of coefficient to the loss function. Here its effect is say penalize large coefficient leading to smaller bit, which makes the model simpler and more robust. L theta is equal to loss plus lambda into theta square. When you want to prevent overfitting without eliminating any features completely. Elastic net regularization. So combination of L1 and L2 regularization balancing between both penalties. It encourages both feature selection from L1 and small coefficient from L2. So loss function here, loss plus lambda 1, say theta 1 plus lambda 2 into theta square. Use case when you want a balance between eliminating irrelevant features and reducing the effect of say large coefficient. What is a dropout regularization techniques? During technique randomly drops that is set to 0 a fraction of say neurons in the network. This forces the model to learn a redundant representation and prevent neuron from co-adapting too much. It is used in say deep learning model, particularly in say neural networks. Early stopping, stop training the model once the performance and validation set start to decrease, even if training loss continue to increase. Then we are having say data augmentation and regularization by artificially increasing data data set side introducing variability. So then we are having norm constrain the beta model to have a limited norms L1, L2 or max norm, ensuring that no single bit become too large. Then here consider a simple data set where one feature x and other binary feature y. Find fit a logistic regression model to this data. Here we are having say features which is given by x, target which is given by say y. Next here, logistic regression. So it is given by 1 by 1 plus e raised to power minus of wx plus b. Let us assume say w as say 1 and bias value as say minus of 2.5. So when we put all these value here for x is equal to say 1.0. So when we will put all these value, we will get here say 0.18. For x is equal to say 0.2, when we will put all these value here, we will get here say 0.60. Next here x is equal to 3. So we will put all these value here, we are getting here say 0.62. For x is equal to 4, we are getting here say 0.81. Now, if if it is probability is greater than say 0.5, classify as 1. If it is less than 0.5, classify as a class 0. So for x is equal to 1, we are getting here probability say 0.8 it is classified as a 0. For x is equal to 2, we are getting probability as a 0.60. So therefore we classified this point as class 1. Similarly, for x is equal to 3, we classified as class 1. For x is equal to 4.0, we classify as a class